So, welcome to third lecture on network analysis, and we have been discussing about sources, and we have seen that ideal voltage source is like this, and a practical voltage source is like this, some internal resistance. It is like this, and these are the two terminals of the source, and this is the EMF of the battery. And the characteristics of an ideal voltage source, if you sketch that it will deliver a current I. So, this axis is suppose I, this axis is suppose voltage VAO. I am sketching potential of A with respect to O, and it will be VAO will be constant at T. This is the characteristics, no matter how much current you draw. How much current you draw is decided by RL connected across the set, across this battery. So, RL can be reduced and larger current should be drawn. Of course, I should not reduce RL too much, so that it exceeds the rated current of the battery, but this will be the VI characteristics of this one. And of a practical voltage source with an internal resistance, this will be this one, this we have seen. Now, in the same line, we have a current source, a practical current source can be represented like this, and here is some current I, fixed current I, and this is the thing, and this R is said to be the internal resistance of this. This E, in both the cases, this portion is ideal, is not, no internal resistance here, this is this. Similarly, this current source somebody draws like this, it means this current will be constant, and a practical current source can be represented in this way with some internal resistance, and an ideal current source will be represented in the, instead of writing ISC, I will simply write now I, how much current it will deliver. To understand that one can interpret instead of a voltage source, a current source is present, that ISC is equal to E by R was brought in, but once that is done, I can think of this thing like this AO. Therefore, the characteristics of a ideal current source, if this is I, this is I, and this is voltage, and here you will connect load RL. It says that whatever is the strength of this current source, that current that current will remain constant at this value I. Voltage may change between this A point. For example, if you have a 2 ampere current source, somebody says ideal current source, connect RL. If RL is equal to 1 ohm, the voltage across this will be 2 volt. If you connect 4 ohm, RL is equal to voltage across it will be 8 volt. That is why voltage can be anything. Of course, anything means it should not disturb the insulation level of RL, so that it will be destroyed, but there must be some RL should be connected here, and voltage can be anything. So, this arrow indicates a current source, ideal current source is such that if it is connected in a circuit, this branch current gets fixed, no matter what will be the voltage across this. So, this voltage will be unknown. In case of an ideal battery, the voltage is fixed, current could be anything decided by RL. Understood? Therefore, a practical current source can be thought of as an ideal current source in parallel with a resistance. Then this resistance can be thought in as a part of this whole network that you will connect across AO. It looks like that then. See, a practical current source, this portion is ideal current source. And then this R and other impedance connected across this R can be thought of part of this. Who prevents you to do that? And therefore, voltage across it will be decided by this I and this equivalent resistance. It could be anything depending upon the value of RL. RL may change, load resistance, but internal resistance of the current source will not change. Therefore, depending upon the strength of the current source, the characteristics will be like this. Voltage can be anything, VAO across a current source. Now, one important thing, although it is still, I am telling you, repeating you, I am not sure about the practical availability of the current source. From concepts we are trying to develop the property of a current source. It must do like that. Therefore, it looks like this point is very important. Suppose there is a practical current source 2 ampere. Suppose it is available with two terminals A and O. Should I keep it open circuited? That is the first thing we must understand. If it is available, this current source will always try to drive a current of 2 ampere in this branch. With no load resistance connected, A and O, it is suppose open circuited, then also it will try to drive a current 2 ampere. It means that open circuit means what? RL tending to infinity, is not? Then only these 2 points will be open circuited. Therefore, it looks like a current source, if kept open circuited, what will be the voltage between these 2 points then, A and O? 2 into RL, and RL tending to infinity. So, infinite, very large voltage will appear. Therefore, it looks like if a current source is really available, then it should not be kept open circuited, because across A and O then high voltage will exist, which may be very dangerous to the persons who is using the current source and making a circuit like that. It should not never be open circuited. Instead, a current source, ideal current source, which has got no internal resistance. No internal resistance means infinite internal resistance. This should be kept shorted. Shorted current source terminals should be kept shorted when not in use. An ideal voltage source should be kept open circuited between A and O, open circuited. When not in use. Because I know what is the voltage. This is the difference between and for that I do not require big theories. I understand if somebody insists that a current source is a fellow which always tries to drive a current of 2 ampere no matter what impedance you connect across it, then it looks like if you keep it open circuited, that means R L connected between A and O is infinitely large open circuit. Still it will try to force a current of 2 ampere, then large voltage will appear which will be dangerous to the persons who will be handling this current source and so on. So, current source when not in use should be kept short circuited. Okay. Therefore, to use a current source, a practical circuit will be like this 2 ampere, suppose current source. Your switch should be parallel across the load resistance R L, ideal current source. When you do not want to deliver power to R L, it should be shorted. What is the voltage between these 2 points? 0. 2 ampere will circulate here, because it is 0 resistance shorted, no power is delivered to the load. When you want to deliver power to R L using this current source, open this. Therefore, you see if you imagine all sources available are current source, then to energize a circuit your switch should be parallel across the load like this. When to be in use, you open it, 2 ampere will flow. Anyway, these are very interesting things and should be understood. So, a practical current source will consume certain current here, but an ideal current source does not consume anything, total current it delivers. You can sketch the voltage versus current characteristics of a practical current source. It will be I when no load is connected, but it will be slightly less current. This will be the characteristics, because this load current I will be I minus this internal current of the current source. So, it will be somewhat like this. I think you have got the point. With this in mind, we can proceed further. So, I will then say that in a circuit there may be sources, and till now I am considering sources which is not a function of time. If it is voltage, fixed voltage source. If it is current source, it is a fixed current source, and so on. And if it is a battery, ideal battery, the voltage across the battery is known, nothing to be found out. Current will be decided by whatever impedance you connect. If it is an ideal current source, current in that branch wherever that current source will be present, that is known, but voltage is across the current source is to be calculated from the whatever impedance or resistance we have connected in the network. Let us consider a very simple example. We go slowly here. For example, let us consider a network like this. a battery and a say current source 1 ampere I write, and when I have drawn a current source like this, I have told it is an ideal current source, and there is suppose another resistance in this circuit. I want to find out the current in various parts of this circuit. And let us take simple example, say this is suppose 2 ohm and this is suppose 4 ohm, like this. Acha. Now I have formally not defined what is a loop, what is a mesh. I have not done anything like that. Still, as if I am in school days, I know KVL, KCL. Based on that, I will solve this circuit. Now, first point is what I have been asked. There are two sources. One is a 10 volt ideal voltage source, 1 ampere current source is present, and these two resistances are known. Problem is to find out the currents in all the branches in the circuit. That is what I have to find out. One point which is not, I will not say it will add to your knowledge, but one thing is clear, since you have to find out currents in all the branches, I will be happy to see in a circuit current sources present. Why I am telling this? Because in that case this branch current is already known, 1 ampere. What to find out? There are this branch, this is another branch, these currents are unknown, but in this branch current is already known. So, to find out, that is, you should not be upset because of presence of many current sources present in a circuit. Rather, I will say if more current sources are present, at least your labor is going to be less to find out currents in other branches, because those branches which are hosting current sources, those currents are already known. Because network problem is essentially source voltage, source currents will be known, you have to find out the currents in various branch. In that simple way, if you look at, then I will say, look here in this circuit, this branch current is already solved for me. Because of what? Because somebody is telling there is a constant current source 1 ampere. Now, how to solve this current? I will solve this current in this way. Now, while solving this current by using KVL, KCL, what I will do is this, I will assume this currents. For example, this current I say this is I ampere. Then I come to this point and I find at this junction KCL has to be satisfied, and this fellow, this branch current is 1 ampere. So, this current must be I minus 1 ampere, is not? This is what I will try to find out. So, there is one unknown, small I, that I have to find out. So, KCL I have already applied. Now, I have to apply KVL. KVL is this one. This exercise, please go through it very carefully. KVL is true for any closed path. In this path, this voltage and voltage between these 2 points, suppose this point is A, this point is O, sum of these voltages must add up to 0. Similarly, in this path, this voltage and this voltage must sum up to 0, all things are known. But you see, the voltage across the current source is unknown. That is, whatever will be the voltage drop across this one, I am not sure. That is another unknown x volt. because as I told you, current source delivers constant current, but the voltage across it, that is between these 2 points, will be decided by these impedances and other things connected across the current source. So, that voltage is not known when you start solving a problem, and this is not surprising. In ideal battery case also it is like this. In a circuit only having batteries and other resistances, voltage across the battery is known, but how much current it is delivering is decided by the impedance connected. So, the converse thing is with the current source is that it is delivering a constant current in this direction, with this arrow indicates that, but unfortunately the voltage across the current source is not known. Acha, anyway, but the KVL is will be satisfied in this loop, and also in this loop, in this outer closed loop. Any closed loop you take up and KVL will be satisfied. So, I is the unknown. So, let me take this loop O, say B, C, A, D, O, this loop. I will take the loop I will start my journey from O, then I will go to B, then I will go to C, then I will go to A, then I will go to D, and then I will come back to O. This is the loop let us consider. Acha, second important point is the moment you have assumed the direction of the current, I write down the voltage drop across this 2 ohm resistance with this polarity, because I have assumed like this. So, this side is plus, this side is minus, and this voltage drop is 2 I. Similarly, I have assumed the current to flow from top to bottom, which is I minus I, and I will write down the voltage drop here with this sign as 4 into I minus 1, that is all. Then I take loop this and apply and write down KVL in that KVL and write down KVL in this loop obviously. So, start your journey from O to B, no voltage drop, 0, then B to C. Yes, there is a voltage rise minus to plus. So, write down plus 10 volt. Then C to A, plus to minus of what magnitude? Sorry, excuse me, 2 I, plus to minus. Then A to D, no voltage drop, because no resistance here, no battery etcetera present. Then from D to O, yes, there is a voltage drop minus 4 I minus 1, and then after that you reach O. This point and this point are same O. And KVL says me that this is equal to 0. So, here is one unknown, one equation. So, I just solve this equation. So, 10 minus 6 I plus 4, is it, is equal to 0, or 6 I is equal to 14, is it, or I is equal to 14 by 6 so much ampere. How much it is? 14 by 6 ampere, if everything calculated is okay. Say 2.33 ampere is this current. Then what I will do is this, I will redraw the circuit, although it will not be necessary as you become more familiar with the system, but it is to begin with, it is always better after you have solved the circuit, redraw the circuit like this. Here was the current source 1 ampere, and here is another resistance 4 ampere. Then this is 10 volt, and now I have solved the circuit, and this I has come out to be positive. So, this current is 2.33 ampere is flowing, and then I apply I minus 1. So, 2.33 minus 1, this current will be 1.33 ampere, this will be the thing. Now, you see, as I was telling, VAO will be how much? I can now calculate. What will be the voltage across the current source? It will be start from O, try to reach A. Via this path, if you go, you cannot fish out anything, because that voltage is the unknown thing. So, if you go via this path, it will be equal to this voltage is 4 into 1.33, is not, this voltage will be this plus minus. So, how much it is? 4 into 1.33, 5.33 volt, is it? So, this VAO will be 5.33. So, you see the voltage across the current source for this particular example is 5.33. If you change this resistance to some other value, it will have some other voltage. So, this voltage is this one. And what will be the polarity of this voltage? Mind you, the polarity of the voltage, because this is this plus, so this is plus, this is minus, is not, this will be the polarity of the voltage. Now, let us do that power audit in this networks, which we have learned earlier, that in any network after you have solved, the total power supplied to the networks is bound to be equal to the power losses in the resistances or impedances, whatever it is. Now, at this point I must say that resistances are such elements which will always dissipate power. No chance that a resistance will give out power, a positive value of resistance I square R. Whatever power comes to the resistance, it is immediately dissipated as heat and lost forever. In any case, we will see that. What is the voltage drop here? 2 into 2.33, how much? 4.67 volt approximately, okay. And this voltage is known, and this current is 1 ampere. Acha, let us take this 10 volt source. What it is doing? 10 volt source. This current is 2.33, through the plus terminal it is coming out. So, this 10 volt is delivering power. How much power? 20 into 2.3367, sorry, 10 volt into 2.33, okay, I wrote correctly, 2.33, how much what? 10 into, sorry, 10 volt into 2.3, how much what? 23.3 watt. So, this battery is delivering power, mind you, right, delivering. Acha, what this current source is doing? Let us see. Current source is having a voltage drop across it, which is equal to 5.33 volt 4 into 1.33 with this side plus this side minus, and current is so through the plus current is entering. So, this current source is absorbing power. So, current source absorbs, I will write absorbs. How much power? The voltage across it, that is 5.33 into the current, that is 5.33 watts. Who are the other fellows that are absorbing power? This resistance and this resistance. So, I will write, please bear with me since I am writing this here, there. So, power absorbed by resistances will be how much? 4.67 into 2 plus 4 into 1.33 into current, sorry, 2.33 is not, this is the thing. So, this is 2.33 plus the power absorbed by this resistance is 1, this is 4 ohm, I think, is it? This is ohm. Please correct that, this is not ampere, sorry for that. So, this is ohm. So, 4 into 1.33 is the voltage into 1.33. So, how much it is? Oh, this is 5.33. So, 5.33 into 4 into 1.33. So, how much this sum becomes? 18 watt. Acha. Then the total power absorbed will be resistance absorbs power, this resistance absorbs power, that is 18 watt. So, I will write total power absorbed power has been absorbed by this resistances 18 watt plus the current source 5.33, which will be equal to 23.33 watts, and power delivered by the source is also 23.33. So, everything is fine in this circuit, got the point. Therefore, what in essence I am telling is that in a network there may be different types of elements. We have started with simple things, resistances are present, and there may be voltage source, current sources which are present, and I have now told you that if current sources are present, then in whichever branch this current source is present, that current is known, nothing to be solved here. This 1 ampere is conditioned by the presence of this current source as 1 ampere. So, you have to solve the other currents, but voltage across the current source I do not know. After I have solved this circuit, then I discover that for this particular load and for this circuit VAO is 5.33. So, it is the voltage across the current source which really needs to be calculated. Then after I have solved this circuit, I have done that power audit once again for this circuit. See, in this circuit resistances will absorb power or energy, and that power must be supplied by some sources. not that all the sources will deliver power. Here is an example, this current source does not deliver power, it absorbs it, and this battery delivers power. So, this exercise is very much educative, and please solve on your own this kind of problems, and always try to verify after you have solved the circuit that okay, KVL is satisfied in this loop, in the outer loop, and also power balance exists. If power balance does not exist after calculating, you must be wondering something must have gone wrong in your calculations. Okay, we will continue with this in the next class. Thank you.